When was the last time NASA released images from the James Webb Telescope? And did Hubble capture something extraordinary before suddenly going silent? This is the worrying reality surrounding Bi-Atlas, the third confirmed visitor from interstellar space. Part 1. The missing images alas appeared in July, with features that raise more questions than answers. And in the early weeks, we received regular updates along with stunning images. But everything changed completely in August when Hubble went silent, while Webb's spectrometer fell into an unclear analytical state, and NASA only issued general, overly streamlined updates even as Atlas approached Mars. The organizations we trust in the extraordinary withdrew behind a wall of silence. This raises the question, what is really happening behind the curtain? And what have they discovered that they are not telling us? In tonight's exploration program, we will delve into the angry theories behind the absence of new images, along with the most terrifying possibility that no one mentions something is wrong. And as of 22/9, the most recent public releases from the main telescopes show a worrying timeline. Hubble's last photo of Bi-Atlas was taken on 21/7, but was not released until 7/8. Meanwhile, the James Webb Space Telescope only observed the object on 6/8 and only published spectral notes. The silence was broken only by a photo from the Gemini South Observatory released on 4/9, but even this photo was taken on 27/8. This makes us reflect. Our most powerful eyes in space have been almost silent about the most interesting object to visit the solar system in many years. NASA's official page on Bi-Atlas offers a convenient explanation. Observation capability will decrease after September, as the comet approaches too close to the Sun from Earth's viewpoint, leading to solar conjunction, making observation difficult. This is a completely reasonable explanation with a solid scientific basis that should reassure us. But does it really explain the shortage of images that we are experiencing? No. Let's consider the timeline that could make anyone following space exploration worried. 21/7. Hubble took the last public image of Bi-Atlas. 6/8, Webb observed the object but only published spectral data. Late August, Gemini South took images, which were not released until early September. As of 22/9, the public is still waiting for new images from the leading telescopes for nearly 2 months. The relative silence from the instruments we rely on to see the wonders of the universe is worrying. A frightening theory has spread in some circles suggesting this silence is not accidental. What if something too strange, unprecedented, and hard to explain was recorded during those missing weeks? What if those images exist but are being withheld because they challenge everything we know about comets, about extraterrestrial visitors, and about what might happen in the dark void between stars? However, we must be fair to conventional explanations. Telescope time is very precious and usually scheduled months in advance. Also, the analysis processes for major observatories are slow and careful because scientists want to understand what they are seeing before sharing it with the world. And spatial geometry is very harsh. Sometimes objects are simply unobservable from Earth's viewpoint. These are reasonable reasons for any gaps in coverage. But reports we have from mid-September describe something extraordinary faster than predicted, brighter, and of a magnitude far beyond what models suggested. These claims come from amateur observations, and their estimates of brightness being 20 times greater than expected, have not been confirmed in peer-reviewed papers, possibly due to observational errors, equipment differences, or measurement inconsistencies. But if not, then the comet's flyby of Mars on 310 is only days away. If space agencies have new data, if they have recorded something remarkable or unsettling during those missing weeks, time is running out. Mars represents the best. If they had recorded anything remarkable or unsettling during those missing weeks, time is running out. Mars represents the best opportunity, perhaps the only chance to observe up close and obtain actual data that can confirm or refute the spreading hypotheses about this mysterious visitor. The public deserves to consider the real science alongside the frightening speculations, deserves to see all the evidence, both reassuring and worrying, and decide for themselves what we might be witnessing. The question is not whether scientists are hiding something, but whether the silence itself has become more revealing than any possible images. We have seen how previous interstellar visitors were handled, buying, dominating headlines with continuous updates. Photoshop became a media favorite with steady streams of images and data. Atlas is different, reporting more cautiously and moderately. More carefully, at the upcoming interstellar visitor, the Mars orbiters may break this silence with close-range observations that could change everything. But the question is whether those images, when they appear, will be shared with the transparency we expect, or whether a selective silence model will continue to leave us wondering what wonders or horrors are hidden from our view of the universe. Part 2. What We Know So Far, by Atlas. Emerging from the cosmic darkness on 1/7/2025, detected by the Atlas survey system and the confirmed second visitor to our solar system, after the mysterious Oumuamua and the usual cometary interstellar visitor Photoshop. But Atlas has proven to be something completely different. A cosmic puzzle wrapped in a frozen gas cloud. Its orbit brings it worryingly close to Mars on 3/10/2025, with a closest approach of about 30,000 kilometers, or about 19 to 20% of an astronomical unit AE. The European Space Agency ESA has confirmed that their Mars orbiters will attempt to observe during this encounter, including Mars Express EXO, Mars Trace Gas Orbiter, and possibly even NASA's Mars Reconnaissance Orbiter. If geometry allows, this is the best chance, perhaps the only chance, to capture high-resolution images of Atlas before it continues its journey towards the Sun. Perihelion, the closest approach to our star, comes at the end of October, specifically from the 29th to the 30th, at a distance of approximately 0.36 to 0.4 SU, just inside Mars's orbit. This is where cometary visitors usually put on their best show, where the sun's heat drives spectacular outgassing events, creating the tales we associate with these cosmic wanderers. But Atlas has defied all expectations for Earth safety. NASA has made it clear. This object poses no threat to our planet, with its closest approach to Earth expected in December, about 1.8 farther than the Sun. So we are spectators of this cosmic play, not participants in any collision scenario. But what makes Atlas truly extraordinary lies in its composition and behavior. The SphereX mission detected something unprecedented. A CO2 halo covering about 348,000 kilometers, To visualize, this gas layer is half the radius of the Sun, and no comet has ever been recorded in history with such a giant CO2 halo. The morphology, shape, and structure of Atlas challenge conventional cometary behavior images from Hubble and ground-based telescopes reveal a sunward directed jet, a tail pointing straight towards our star instead of away from it. This contradicts basic physics we teach about: solar wind pressure and radiation affecting comet tails, suggesting something about Atlas's dust grain size, its rotation, or internal structure is creating patterns we do not understand. Reports began appearing in late August and early September, noting a color change. Observers recorded a blue 6 hue developing in Atlas's coma, possibly due to cyanogen or cyanide compounds activated by solar radiation. But this is when the mystery deepens. This blue 6 has not yet been definitively confirmed through spectral analysis, so we rely on visual observations, photographic evidence, and well-founded speculation about chemical compatibility, which may or may not match reality. The brightening trend has become the most worrying aspect of Atlas's behavior. Sky and other astronomy channels have compiled reports from observers noting a faster-than-expected brightening as the object moves inside about 2 AU from the Sun. Not essence. Numbers vary significantly depending on aperture size, filter used, and observing conditions, but this uncertainty is not unusual, as amateur astronomy often produces discrete data points requiring careful statistical analysis to interpret discrepancies in brightness. Measurements reveal a deeper problem. Many of our most recent images come from amateur astronomers stacking multiple exposures to reveal faint details, while the leading telescopes should have provided definitive data. Their data processing procedures proceeded unusually slowly, especially when celestial bodies approach conjunction with the Sun, making observation technically and scheduling-wise challenging. The data release created a perfect storm of uncertainty, while amateur astronomers shared their latest photos on social media. Within hours, professional observatories can store data for weeks or even months during peer analysis and review. The gap between citizen science and institutional astronomy has never been more apparent than with Atlas. Scientists from the European Space Agency have pointed out that spectral data from 6 out of 8 observations by the James Webb Space Telescope are still under review and analysis. They are finding that the spectral lines and chemical signatures appear too complex, requiring extended study before publication. The silence surrounding these results has sparked speculation that something unexpected, perhaps unprecedented, has been discovered. Atlas's orbit closely matches the ecliptic plane, the disk region where planets orbit our Sun. This position allows a close encounter with Mars and sets up a future flyby of Jupiter in 2026. Such precise alignment with our solar system's architecture leads some observers to see more than coincidence. Although orbital mechanics can produce surprising geometries through natural processes, as we stand on the threshold of a Mars flyby, the accumulated data and mysteries of Atlas create an atmosphere of excitement mixed with unease. The lack of images from our most powerful telescopes, the unprecedented scale of the CO2 atmosphere surrounding it, the strange reversed tail, and the uncertain brightness variations, Each piece of evidence alone might represent an interesting but explainable cometary phenomenon. But combined, they form a pattern that challenges our understanding of the shape of these visitors to Mars, what the BA part at Mars should look like. Silence is important. Memory often deceives us, especially when we are accustomed to constantly receiving space images. Recall the WISE comet NEOWISE in 2010 when social media was flooded nightly with photos of its spectacular tail, twisting across the Earth's sky. Or remember the specimen from asteroid Bennu returned and recorded in real time through hundreds of images as the OSIRIS-REx spacecraft approached, touched, and departed its target. Space exploration has made us expect visual documentation of every major cosmic event. Atlas is different. Public releases from Hubble and Webb are very sparse, carefully curated, and since August, leading observatories have maintained what can only be described as an image fasting. This is not unprecedented as telescope time is precious, and not every observation becomes a press release. But for an interplanetary visitor as clearly significant as Atlas, this silence is frightening. NASA's own documents have publicly acknowledged a gap in observational capability. After September, due to dazzling sunlight, the sun's position makes Earth-based observation difficult or impossible during certain periods. This sets reasonable expectations for any data scarcity phase, but it also creates something more dangerous: an information void quickly filled by conspiracy theories. The human mind hates uncertainty. When official channels are silent during high-interest periods, alternative explanations multiply on online forums and echo chambers on social media. The lack of new images from Hubble becomes evidence of a cover-up and delays in results. Webb's spectra turn into proof that something too strange for the public to accept has been discovered. Reasonable explanations for observational gaps lose out in the battle against extraordinary possibilities. The European Space Agency and other international partners have released Gemini South images taken on 27/8 shared with the public in early September prove the astronomy community is not completely silent about Atlas. But the public has grown used to expecting the steady rhythm of portrait steps from Hubble and infrared revelations from Webb. And when those sources go silent, even briefly, it feels like abandonment. Media news samples reveal another aspect of the silence while news about Atlas peaked in July and August. September saw a notable shift in focus to other celestial objects, with the increased brightness of Comet Lemon dominating the headlines, and the fragmentation of Comet Swan, providing impressive images for Atlas watchers in particular. This diverse coverage might feel like a deliberate distraction, although it likely reflects the natural ups and downs of astronomical news cycles. Conspiracy thinking thrives on cognitive patterns when many unusual events occur simultaneously, and the unusual behavior of comets reduces the coverage scope of astronomical media. Attention shifts elsewhere, with minds seeking patterns connecting points that may not actually be related. Unfortunately, the timing of Atlas's opposition cycle coincides with the peak public interest in its flyby of Mars and perihelion passage. Data analysis procedures at major observatories prioritize accuracy over speed. Unlike amateur astronomers who can share images within hours after acquisition. Organized astronomy requires peer review, calibration checks, and careful interpretation before publication. This necessary caution protects scientific credibility, but creates gaps that hasty speculation fills. Public trust in scientific institutions have become more fragile in recent years, from climate change debates to pandemic response controversies. The relationship between expertise and public understanding has grown more complex as space agencies remain silent during periods of high interest, even for legitimate technical reasons. This triggers existing skepticism about official stories. The issue is not whether NASA, ESA, or other agencies are hiding something dramatic about Atlas, but whether the perception of secrecy has become more harmful than any actual classified information could cause in the social media age. Lack of evidence becomes evidence of absence, or worse, evidence of a cover-up. Note, what the public wants now is simple new images as Alaska approaches Mars, and then perihelion, high-resolution photos showing the current state of the object, evolving atmospheric structure, and any changes in its unusual retrograde tail behavior. And the need for visual confirmation of Atlas's strangeness only grows during relatively silent weeks. What scientists want is detailed spectral analysis, more complex to confirm the chemical composition of the comet's giant carbon dioxide mass, to measure nucleus size and rotation period accurately, along with a clear understanding of the physical processes creating the sunward jets. These goals require careful analysis, time, and often multiple observing campaigns to achieve confidence and results. The conflict between public desire for instant images and scientific need for detailed analysis creates perfect conditions for conspiracy theories to flourish, as each day, without new official images, becomes a data point in arguments that something is being deliberately hidden from the public. Soon, Mars orbiters may provide breakthrough images that satisfy public curiosity, or deepen the mystery and haunting questions. The whole situation is whether those images, when they arrive, will be released with the transparency the public expects, or whether new reasons for caution and delay will arise, prolonging the already excessive silence. Part 4. Post-silence hypotheses. Let us consider possible explanations for the lack of Atlas images with the cold elimination method, starting with common reasons and technical realities governing how our most sophisticated instruments observe the universe. Astronomical angle is the simplest constraint, as Atlas approaches conjunction with the Sun from Earth's viewpoint. Observational geometry becomes increasingly challenging, because telescopes cannot point too close to the Sun without damaging sensitive equipment. For example, the Hubble Space Telescope maintains strict pointing restrictions to protect its camera and spectrograph from solar radiation. This creates observational dead zones where even the most interesting targets are temporarily inaccessible. Q time represents another harsh reality of modern astronomy. Hubble and Webb operate according to observation schedules planned months or even years in advance and require observations by opportunity only for truly extraordinary events. As these requests disrupt carefully planned scientific programs, the threshold to disrupt established schedules is very high, requiring scientifically convincing justification far beyond mere public interest and Atlas, despite being unusual. may not meet the criteria for urgent observation time. Delays in analysis affect every major astronomical discovery. Professional telescopes generate data that require thorough processing, calibration, and interpretation before they can be widely published, unlike amateur astronomers who can share raw images a few hours after capturing them. Astronomical organizations demand peer review and quality control. The James Webb Space Telescope observed Alaska's spectrum on 6/8 is probably still being processed through these analytical procedures, with scientists carefully interpreting each spectral line before drawing conclusions. Operational trade-offs further complicate the situation. Near-infrared spectral data from Webb on 6/8 is only one piece of a larger observational picture, and not every scientific observation produces a newsworthy image. Spectroscopy reveals chemical composition but does not necessarily create visual images. The impressive images the public desires. The gap between collecting scientific data and releasing public images can last weeks or months. But let us delve into more speculative areas clearly marked as such, because these theories have been followed by the online community. Atlas's VI action has received the hypothesis of panic suppression, suggesting space agencies might delay image releases if they are too unusual or difficult to explain without causing public panic. Imagine if Atlas's VI's tail had developed into something artificial-looking or structurally complex in inexplicable ways. Would NASA rush to share such images without first developing frameworks to help the public interpret what they are seeing? This theory assumes a paternalistic approach to information management, where experts filter cosmic revelations to prevent misunderstanding or fear. Considering national security adds another layer of complexity. Military surveillance certainly monitors bright objects like Atlas, possibly with higher resolution and better temporal coverage than civilian telescopes provide. But military data is rarely made public, even for scientifically interesting targets. The gap between classified observational capability and public information sharing creates space for speculation about what enhanced images might reveal. Information control during combined phases offers a more skeptical explanation if agencies anticipate that Atlas's approach to the Sun will cause observational difficulties and public impatience. They may have chosen to wait rather than explain, to better explain technical limitations rather than remain silent until further observations, rather than continuously apologizing for the lack of new images during difficult observation phases, contrary to all speculation, still evident in astronomical records. Both ESA and the Gemini Observatory shared their 27/8 images in early September, proving that complete information blackout about Alaska did not occur. Professional astronomers continue discussing this object at conferences and in papers submitted to journals. The scientific process continues even as public images become scarce. Prioritizing equipment can explain some observational gaps. As Atlas approaches the convergence point, telescope operators may reasonably decide to focus limited observation time on more accessible targets, rather than struggle with increasingly difficult solar elongations. This reflects rational operational planning, rather than intentional concealment. The complexity of international coordination may also contribute to delays in releasing information. Many space agencies and research institutes are independently studying ATLAS and coordinating information release across different organizations, each with peer review processes. And their own public relations rules naturally causes delays compared to releasing from a single source. This analysis clearly shows that the silence around ATLAS probably stems from logistical and operational constraints rather than deliberate concealment. However, the cessation of regular image updates during the period of greatest public interest certainly facilitates conspiracy theories. The gap between reasonable explanations and public perception has become as intriguing as ATLAS itself. The selective information disclosure model in different contexts, since UAP unidentified aerial phenomena reports, has led the public to expect information management rather than full transparency, whether justified or not. This expectation shapes how people interpret the gaps in official communication about unusual events as we prepare for observations of Mars passing by, after many weeks of relative silence have accumulated, creating an atmosphere where any new image will be scrutinized not only for what it shows, but also for what it may have been edited to conceal. The feeling of secrecy, whether real or imagined, has become part of the story about ATLAS. Part 5. Government and Space Control. The space communication apparatus operates through carefully arranged channels, which few outside the astronomy community fully understand. NASA maintains a public mission, but the timing and manner of press releases are carefully selected to maximize scientific accuracy while maintaining public interest. The European Space Agency also follows similar procedures, balancing transparency with peer review requirements and appropriate context. This system works well for routine discoveries, but creates friction during periods when the public is extremely curious about unusual objects. Classified sensors create a more opaque layer in the observation ecosystem. The Department of Defense tracking systems monitor space for threats and debris. Capabilities certainly extend to bright objects like comets and asteroids. These military assets often have superior resolution and time coverage compared to civilian telescopes, but their data is rarely fed into public channels. The gap between classified observational capability and public information creates fertile ground for speculation about images that may exist but remain hidden. The similarity to recent UAP transparency debates makes government acknowledgement of unidentified aerial phenomena follow a carefully managed gradual disclosure model rather than immediate transparency. This precedent shapes public expectations about how extraordinary space events might be handled if military pilots encounter unexplained objects, requiring years of administrative processing before confirmation. No time frame can dominate the release of unusual comet observations. Media focus clearly shifted away from ATLAS in September, although whether this was a natural news cycle or more coordinated editorial decisions remains unclear. Headlines increasingly highlighted other comets, the brightening orbit of Lehman, significant fragmentation of Swan, while coverage of ATLAS diminished despite it approaching Mars. For observers closely following news about interplanetary travelers, this pattern may resemble intentional distraction, although it more likely reflects the media's preference for visually impressive phenomena. easier to explain than complex scientific mysteries. The emergence of Comet Lemon perfectly illustrates this dynamic. Its predicted brightness curve shows the possibility of naked-eye visibility by late October, making it accessible to amateur astronomers worldwide. News outlets naturally focus on objects their readers can observe themselves rather than telescope targets requiring specialized equipment to see, alas. Despite its scientific value, its significance remains invisible to casual comet watchers, limiting its sustained media appeal. The fragmentation of Comet Swan in September provided exactly the kind of dramatic visual content that space media often exploits. It broke up in real time, creating spectacular debris fields and evolving tail structures. Swan offered an immediately understandable spectacle. While the mysteries of ALAS carbon dioxide outgassing, tail dynamics and unusual brightness evolution require more technical explanations to convey their significance. Risk assessment in science communication has become more complex in recent years. Organizations have learned painful lessons about how preliminary findings can be misunderstood and uncertainty distorted when moving from scientific papers to news headlines. A cautious approach to communicating about Atlas may reflect this learned fatigue more than specific concerns about the object itself. International cooperation in space science creates additional coordination challenges. European, American, and other national space programs must balance individual organizational goals with collaborative scientific objectives. Timing public releases to avoid conflicts between agencies' publication schedules naturally causes delays that may seem suspicious to outside observers. The issue concerns sharing protocols. Data becomes particularly relevant for objects like Oumuamua crossing multiple institutional boundaries responsible for communication publicly about an interstellar visitor. How they coordinate with other observation groups to ensure a consistent message. Questions about this process have real impacts on the flow of information to the public. With public expectations of transparency in space shaped over decades, impressive images from missions like Voyager, Cassini, and Mars rovers. Continuous photo streams from these missions have created an assumption that every significant space event should produce similar visual documentation. When that expectation is not met, even for legitimate technical reasons, it creates cognitive dissonance exploited by conspiracy theories. Selective information leaks visible in other government communications certainly affect how people interpret gaps in space agency announcements, whether the topic is national security, public health, or economic policy. Institutions regularly demonstrate that information management is prioritized over full transparency, a well-established pattern. This causes the public to doubt similar filtering in space-related media. Control mechanisms in scientific publishing add another layer of delayed disclosure. Professional astronomy operates through peer review processes that can take months from initial submission to publication of results. Even when scientists have astonishing findings about Oumuamua publication timing, ensures preliminary results remain within the expert community while the wider public waits for official announcements. The intersection between scientific caution and public curiosity creates an inherent tension in how extraordinary discoveries are communicated. Scientists want to fully understand anomalies before making statements that might later have to be embarrassingly retracted. The public wants immediate access to any evidence of strange phenomena in the universe. Reconciling these different timelines requires skill and transparency, which organizations do not always demonstrate effectively as we approach the Mars flyby window. The cumulative model of careful information management around Oumuamua has created an atmosphere where any new release will be scrutinized, not just for what it shows, but also for what may have been edited out to conceal parts. The photographic history of Oumuamua on 19-10-2017 from the Pan-STARRS telescope in Hawaii discovered something impossible. An object moving through our solar system on a hyperbolic orbit, clearly originating from outside space, arriving at Mars within hours. The astronomical community mobilized with unprecedented coordination. Follow-up observations from telescopes worldwide confirmed what would become the most studied single object. In modern astronomy, Oumuamua, our first confirmed interstellar object. Transparency around the detection and study of Oumuamua contrasts completely with the current situation. Data circulated freely among institutions. Light curve measurements appeared on preprint servers within days, and shape reconstruction, rotation period analysis, and orbital refinement were all shared publicly as they were developed. The scientific process unfolded in real time, visible to any AI ready to track technical documentation. What made covering Oumuamua feasible also made it scientifically puzzling. The object showed no signs of cometary activity. No coma, no tail, no outgassing that could complicate photometric measurements or obscure surface features. The absence of comet-like behavior simplified the observational challenge while deepening the mystery of its composition and origin. The famous non-gravitational acceleration detected in Oumuamua's orbit sparked intense debate. But that debate took place publicly. Competing hypotheses appeared in journals and were discussed at conferences broadcast openly. From the hydrogen iceberg theory, speculation about a solar sail, to proposals of a nitrogen ice block. Each explanation generated further observations and analyses shared publicly, allowing the scientific community and interested public to follow the investigation in real time. The Spitzer Space Telescope provided crucial data on Oumuamua's thermal emission, effectively ruling out certain structural models. These negative results were published rapidly, demonstrating how negative findings can also have scientific value like positive discoveries. Transparent handling of Spitzer not detecting this contrasts with the current silence about Webb's spectral observations of Atlas. Light curve analysis shows Oumuamua has an extremely elongated characteristic, shows a shape unlike any known asteroid or comet. These findings appear in multiple papers from different observation groups, create a robust data set supporting reliable conclusions about the object's unusual shape. The redundancy of independent observations has provided cross-confirmation, strengthening public trust in the scientific process. The lesson from reporting on Oumuamua seems clear when anomalies spark immediate public discussion. The accumulation of evidence and competing explanations tend to calm rather than increase speculation, because transparency creates understanding, while information gaps create conspiracy theories. The real-time scientific debate around Oumuamua has demonstrated how public investigation can handle even the most unusual discoveries. But Oumuamua's lack of cometary activity fundamentally distinguishes it from Atlas. No comet tail means no complications from dust and gas that might obscure or distort observations. No gas escaping means no pressure effects that could unpredictably alter the object's orbit. Simpler observational challenges help rapid analysis and feasible publication. International collaboration in Oumuamua research has shown astronomy at its best. Teams from many countries freely shared data, building additional analyses that enhanced overall understanding. This collaborative approach has maximized scientific benefit from limited observation opportunities while maintaining public engagement throughout the investigation. Compare this with Atlas's timeline after August, when major observatories were relatively silent despite the object having much more dramatic cometary behavior. Differences in communication patterns raise questions whether the complexity of Atlas's features require more careful analysis, or if other factors are affecting the speed of information release. Oumuamua followed a trajectory, quickly out of the inner solar system, creating urgency that forced rapid decisions on observation priorities and quick publication of results. Atlas's more leisurely approach when reaching perihelion may remove some of this urgency, allowing more careful analysis timelines but still frustrating public curiosity. Media coverage of Oumuamua has shown both benefits and risks of transparent science communication. Although most news conveyed scientific uncertainty and competing hypotheses accurately, some media sensationalized more speculative explanations. This mixed reception may influence how organizations approach communication of similarly unusual objects like Atlas. Professional astronomy has learned important lessons from the Oumuamua experience about managing public expectations during investigations of unusual objects. Balancing timely sharing of exciting discoveries with avoiding premature conclusions requires careful navigation. Perhaps a more cautious approach with Atlas reflects this learned experience. The timing of Oumuamua's discovery in October allowed wide observation under good conditions, before the object became too faint and distant for effective study. Alaska's discovery in July and approach to solar conjunction in September created a compressed and more challenging observation timeframe that naturally may lead to more cautious communication strategies. However, the fundamental question remains in astronomy. The scientific openness that characterized Oumuamua research has not been applied to the Atlas investigation. This object exhibits phenomena, even more impressive and observable than its predecessor. Yet, public information about its current status is increasingly scarce. The contrast suggests either technical challenges or policy decisions are shaping a more restricted approach to sharing observations. Atlas with the public. Part 7. The Open Book of Borisov. 2019. Gennady Borisov, an amateur astronomer in Crimea, discovered something unusual through his homemade telescope. Within weeks, professional observatories worldwide confirmed his discovery of Borisov, the second interstellar visitor to our solar system, unlike the mysterious Oumuamua. Sodashape behaved exactly as astronomers expected an interstellar comet should behave, and this normal behavior made people feel comfortable when sharing everything they had learned. Transparency around the Photoshop investigation was considered normal, precisely because of this object. Following the established scientific principles about comets, it showed a familiar progression when approaching the Sun. Its coma developed predictably as it was heated by the Sun, and spectral observations showed familiar water vapor and other volatiles escaping according to expected models. Scientists understood what they were seeing, which gave them confidence to share their observations with the public. Images of Borisov from the Hubble Space Telescope appeared regularly throughout its journey through the solar system inside these photos, showing the comet's behavior. Exactly as in textbooks, a condensed nucleus surrounded by an expanding halo of dust and gas, with the tail extending away from the Sun. Under pressure from solar radiation, these images were both familiar and intimate, as well as highly educational parents could show them to their children and explain what they were observing without encountering strange, unexplained phenomena. The European Southern Observatory, NASA, and other organizations continuously issued a stream of press releases about the changing characteristics of Comet Borisov, including estimates of nucleus size, chemical composition of escaping material, and refining the orbit as gravitational perturbations became measurable, each update fully consistent with the current theoretical frameworks. Used to explain comet behavior, spectral analysis showed Borisov's composition was very similar to comets from the solar system's Oort cloud. Water, carbon monoxide, and dust particles were all familiar components, thereby validating theories about planet formation in other star systems. The chemical similarity between interstellar comets and native comets became a compelling scientific story, without any complicated explanations or cautious warnings about unprecedented phenomena, even when Borisov began showing signs of fragmentation in late 2019 and early 2020. This dramatic development also followed well-understood physical laws. Comets break apart under thermal stress and tidal forces. This process, although spectacular, posed no explanatory challenges requiring publication delays or cautious analysis. The fragments behaved predictably, creating beautiful fragment fields, and the difference between Photoshop and Atlas became clearer through this comparison. Ordinary comets generate ordinary public relations strategies, while unusual objects cause analytical difficulties, slowing information flow. When scientists clearly understand what they are observing, they feel comfortable sharing those observations immediately. But when faced with behaviors challenging existing models, scientific caution naturally increases. Professional astronomers have established procedures to handle unusual discoveries, which require more extensive analysis before publication. Peer review processes, which run smoothly for ordinary results, can become prolonged when reviewers struggle to assess claims beyond current knowledge. The more unusual the observation, the higher the publication standards, and the longer the delay before public disclosure. The normal behavior of Borisov also allowed many independent research groups to obtain similar results, thereby building confidence through repetition. When many observatories consistently measured outgassing rates, nucleus size, and chemical composition, the scientific community felt confident sharing preliminary findings. Conversely, Atlas's unique features made independent verification more difficult and increased uncertainty in interpretation. Media coverage of Borisov reflected this level of scientific confidence. Press releases emphasized the educational value of observing an interstellar visitor behaving exactly like a native comet. This confirmed our understanding of planet formation processes across different star systems. Journalists could write about Borisov without needing to interpret complex technical caveats or admit fundamental uncertainties about what they were describing. Public interest in Borisov brought satisfaction because this object confirmed rather than challenged existing astronomical knowledge. The public can learn about comet science by tracking an example related to comets, proving that universal physical laws still operate beyond our solar system. Its story is clearly educational and ultimately reassures us about understanding cosmic processes. Amateur astronomers can also meaningfully participate in observing the body shop, because the behavior of this object falls within familiar parameters. Home telescopes can record the development of the comet's tail, track its light curve, and contribute to the shared data repository in ways welcomed by professionals. This broad participation has created a shared sense of discovery that enhances public engagement. The contrast with the Atlas reporting model becomes clear through this historical comparison, while Photoshop produces regular updates and educational content. Atlas instead creates cautious silences and delays in analysis. This difference is not necessarily worrying. It may reflect the challenge of communicating phenomena that do not fit established classifications. Consider the burden placed on organizations when faced with truly unusual observations. How to explain a coma layer created by carbon dioxide stretching half the solar radius? How do you interpret a tail with behavior contrary to basic expectations about interaction with the solar wind? The complexity in explaining Atlas's features has gone beyond the simple educational opportunity Photoshop offers. Lessons from how everything about Photoshop was disclosed show that transparency in space science strongly correlates with comprehension. Discoveries fitting existing theoretical frameworks make organizations comfortable with broad and rapid communication to the public. Conversely, when observations challenge foundational assumptions, these organizations tend to be cautious, prioritizing analysis and delaying publication. Such behavior certainly raises suspicions about what might be concealed. This behavior raises uncomfortable questions about whether the public is fully informed when information is consolidated, rather than challenging established scientific understanding. We are witnessing the result of natural scientific caution, or evidence of institutional bias favoring safer discoveries over revolutionary ones. Part 8. How Atlas breaks the mold. The scale of Atlas's carbon dioxide shell surpasses all precedents in comet astronomy. The CO2 shell, 348,000 kilometers wide, extends from the nucleus forming an atmosphere larger than anything previously observed. To visualize this magnitude, imagine that this atmospheric region extends about half the solar radius, larger than the orbit of most planets. Historically, no comet has produced such a vast carbon dioxide atmosphere, making Atlas an incomparable phenomenon. Traditional comet models predict that the atmosphere, forms through water sublimation as the object approaches the sun's thermal influence. Carbon dioxide usually plays a secondary role, present in smaller quantities, and creating more modest atmospheres. Atlas seems to have reversed this order, with CO2 dominating the outgassing process to an unprecedented degree. This unusual chemical composition challenges fundamental assumptions about how interstellar objects form and evolve. Its tail, recorded in images from the Hubble and Gemini telescopes, violates basic physical laws as we understand them in comet science. Solar wind pressure should push material away from the sun, creating the classic tail structure shaping these objects in the public imagination. Yet Atlas exhibits completely opposite behavior, a prominent stream of material directed straight towards our sun. This behavior seems as if the object is defying the fundamental forces governing every other comet we have studied. This anti-tail suggests properties of dust particles unlike anything we have encountered. Perhaps the dust grains are so large that solar radiation pressure cannot overcome their inertia. Perhaps electromagnetic forces are interacting with charged particles in ways our models cannot explain. Or perhaps the object's rotation is generating jets of material in directions seemingly contradictory to physical laws. Each explanation requires assumptions beyond the established scientific foundation of comet science. Reports of the comet brightening rapidly in mid-September added another layer in the unusual orbital record of Atlas. An amateur astronomer tracked the object and recorded its brightness increasing far beyond theoretical predictions significantly. Some observers claimed the brightness increased 20 times more than expected, although these estimates have yet to be confirmed through professional analysis. The discrepancy may reflect measurement errors, equipment differences, or changes in observation techniques rather than actual anomalies. But if those brightness reports are proven accurate, then a comet star brightened faster by 20 times than model predictions, indicating processes occurring inside or around the nucleus that our understanding cannot explain. Perhaps the acceleration rate is increasing beyond the usual thermal limit. Possibly the internal structure is exposing new volatile materials to the sun's heat, or perhaps the object is undergoing fragmentation, or structural changes increasing its effective surface area. The color changes observed in late August and early September added a dramatic visual element to the growing list of Atlas's unusual features. Photographers began recording a distinct blue-green hue in the coma surrounding the comet star, possibly due to compounds released from gas or dust excited by solar radiation. These chemicals commonly appear in comets, but their prominence in Atlas suggests an unusually abundant presence or an enhanced excitation mechanism. The temporary nature of this blue-green identification also suggests another worrying aspect in the investigation of Atlas. Visual observations and photographic evidence showed chemical signatures that should be easily confirmed by spectroscopic methods. However, definitive spectroscopic confirmation remains absent from published information, despite many observatories having the capability to resolve these questions. It is certain that Atlas's orbit passes through the inner solar system along paths seemingly arranged to maximize observation opportunities. The close encounter with Mars on 310 positioned many spacecraft in orbit to conduct unprecedented close-up observations. Perihelion, at the end of October, occurs at a distance providing optimal conditions to study the comet's evolution under solar heat influence. Its alignment with Earth creates observation windows seemingly designed to maximize scientific benefit. This geometric convenience leads some observers to consider it more than coincidence. Although orbital mechanics regularly produce alignments, surprisingly, through natural gravitational interactions between Atlas, the Sun, and planets, the object may naturally be guided through orbits optimizing observation chances without any artificial intervention or direction. Managing public expectations becomes extremely important when dealing with objects with unusual orbits like Atlas. The public, accustomed to periodic space image releases, will naturally expect more material as objects become more interesting. The inverse relationship between Atlas's increasing strangeness and the decreasing amount of publicly available imagery has created a perceptual dissonance, fostering conspiracy theories about deliberate information concealment. Professional analysis processes slow down when faced with data that do not fit established categories. Reviewers require more time to evaluate claims challenging existing knowledge. Journal editors demand additional verification when papers describe unprecedented phenomena. The more extraordinary the observation, the longer the review process and the greater the delay before publication. The responsibility to explain Atlas's features weighs heavily on organizations that may feel unprepared for the complexity of the issue. How do you communicate about an object that seemingly violates many aspects of established comet science? How do you maintain scientific credibility while acknowledging fundamental uncertainties about what you are observing? The challenge of educating the public about truly unusual discoveries may exceed the communication capabilities typically deployed by space agencies. International coordination becomes more complex when handling observations crossing scientific boundaries. Different organizations may draw different conclusions from the same data, creating potential conflicts, requiring diplomatic solutions before wide publication. The European Space Agency, NASA, and other organizations must balance individual and organizational interests with collaborative scientific goals while managing public expectations at the time of Atlas. The closest approach unfortunately coincided with observational difficulties, increasing the challenge in communication. The conjunction with the Sun limited observations from Earth precisely at the time when public interest peaked around its flyby of Mars and perihelion passage. The time lag between optimal observation conditions and maximum curiosity created perfect conditions for speculation about what might be hidden during the signal loss period. Consider the implications if the unusual features of Atlas are proven to represent a genuinely new physics, rather than just an unusual but explainable cometary behavior of the comet. Detecting phenomena challenging fundamental assumptions about interstellar objects will require a careful analytical approach before public disclosure. The importance of making such announcements accurately can justify prolonged analysis phases that may seem suspicious to outside observers. However, precedents set by Oumuamua and Borisov show that truly revolutionary discoveries benefit from transparent scientific investigation in real time rather than secretive analysis. The public debate around Oumuamua's non-gravitational acceleration ultimately strengthened rather than weakened public understanding of the discovery process. The more limited information flow about Atlas ran counter to that successful transparency model. The fundamental question is whether the silence about Atlas reflects necessary scientific caution, or institutional fear of public reaction to discoveries that might challenge established worldviews. Both explanations carry profound implications about how extraordinary space discoveries will be communicated in the future, and whether the public will continue to be trusted partners in humanity's journey to explore the mysteries of the universe. Or 09 distraction theories. September brought a strange shift in astronomical focus that space media followers could not help but notice while Atlas approached its most scientifically interesting phase, the flyby of Mars and perihelion point. Thereafter, public attention was systematically redirected to other celestial bodies, those bodies offering more conventional and accessible cosmic displays. The spectacular fragmentation of Comet Swan in early September provided exactly the kind of spectacular imagery that space press craved. This object disintegrated in real time, creating debris fields and evolving tail structures that amateur astronomers could capture with home telescopes. NASA's Astronomy. Picture of the Day has repeatedly featured images of Comet Swan showcasing the beautiful destruction of a comet, behaving exactly as textbook physics predicted. This timing seemed convenient for those AIs seeking alternatives to news about Atlas, just as questions about the unusual behavior of the interstellar visitor reached their peak. Swan provided an engaging distraction that did not require complex explanations or uncomfortable admissions about scientific uncertainty. The public could watch a comet die in understandable and predictable ways, rather than puzzling over anti-science tales and unprecedented carbon dioxide coma layers. The new comet Neo-Ice Lemon emerged as another convenient focal point for astronomical attention in September. Predictions suggested this object could reach magnitude 24 by late October, potentially becoming visible to the naked eye for observers worldwide. Media naturally gravitate towards phenomena their audiences can experience firsthand, rather than mysteries seen only through telescopes, accessible only to experts with sophisticated equipment. The promotion of New Ice Lemon created an accessible astronomy story, completely contrasting with the technical complexity of Atlas. The public could step outside and possibly see Neo-Wise Lemon with their own eyes, while Atlas remained an abstract concept, supported only by hard-to-interpret images from professional observatories. The psychological appeal of participating in astronomy, compared to passively receiving expert analyses, is obvious. Starwalk, Sky and Telescope, and other astronomy publications shifted their October comet coverage focus after the predicted performance of New Wise Lemon. Observation guides, search charts, and photography tips flooded online astronomy communities, creating eager anticipation for a promising object. There will be a conventional comet planet. The implicit message here seems to be that the public should focus on the comets they can see rather than worry about an object they cannot comprehend. For those following Atlas, this awareness is unmistakable. Attention is being deliberately redirected towards safer and more familiar targets in the sky. Whether this is a deliberate coordination by editors or just a natural behavior of the media when prioritizing more accessible stories over complex ones remains unclear. However, regardless of the intent, the end effect is the same. Public attention shifted away from Atlas just as its most interesting features were beginning to emerge. Media psychology provided plausible explanations for this change in coverage. Without resorting to conspiracy theories, journalists naturally prefer stories that their audiences can engage with directly, rather than abstract scientific puzzles requiring extensive technical explanation. Visible comets, to the naked eye, generate more reader interest than objects only observable through telescopes, as they create a personal experience rather than learning mediated through expert interpretation. The business model of astronomy. Journalism also values accessibility over complexity. Articles about objects that amateurs can observe with their own equipment generate more social media interaction, website traffic, and reader attention than analytical pieces, requiring specialized technical knowledge to understand. Publishers who respond to audience metrics will naturally emphasize the new ice lemon comet over Atlas. Regardless of any coordinated editorial plan, educational institutions face similar pressures when choosing which space events to highlight in their community outreach programs. Planetarium shows, university lectures, or science museum exhibitions gain more benefit by featuring phenomena that visitors can observe directly rather than abstract concepts. The complexity of Atlas makes it an unsuitable topic for public education compared to conventional comets like New Ice Lemon. However, the timing of this news shift seems suspiciously convenient for any AI wanting to minimize attention on Atlas's unusual behavior, just as the unprecedented features of this object raise uncomfortable questions about gaps in scientific understanding. Alternative targets have appeared to attract public curiosity about comet phenomena in general. Professional astronomy conferences in September also showed a similar emphasis pattern. The number of presentations on the fragmentation of Swan and the brightening of New Ice Lemon far exceeded discussions about Atlas, despite this interstellar visitor having far greater scientific significance. Whether this reflects true research priorities or merely strategic media choices remains unclear to outside observers. Social media algorithms have also contributed to attention shifting in ways that seem coordinated, but actually reflect automated interactions. Optimized posts about visible comets generate more shares, comments, and views than technical discussions about spectral analysis or the physics of anti-tails. Platform algorithms naturally promote content that creates higher user engagement, thereby artificially emphasizing accessible astronomy regardless of its scientific importance. The European Space Agency's media strategy in September strongly focused on other missions and discoveries rather than updates about Atlas. Achievements in Mars. Exploration revelations from the Webb telescope about distant galaxies and results from the Gaia spacecraft dominated ESA press releases. This occurred while their Mars orbiters were preparing for the encounter with the most important interstellar visitor in human history. The contrast between preparation activities and public media priorities seems stark. Amateur astronomy communities showed interesting divisions in their September discussions, while some forums remained focused on tracking and photographing Atlas. Other forums shifted to preparing to observe New Ice Lemon and recording Swan. This division may reflect different community priorities between scientific interest and aesthetics, but it also disperses focused attention, which Atlas attracted at the most favorable observation time in August. The distraction theory becomes more credible when considering historical precedents in managing public attention during sensitive discoveries. Government agencies often schedule announcements that could be controversial alongside other news events likely to attract media attention, while space agencies usually operate with greater transparency than other organizations. They also face similar pressure to manage public reactions to discoveries that might cause confusion or concern. Whether deliberate distraction or simply a natural development of the media. The shift in astronomical reporting in September achieved the same result, reducing public scrutiny of Atlas. During its most critical scientific phase, this object approached Mars, undergoing heating as it reached perihelion and likely revealing its true nature, while public attention was focused elsewhere. This timing raises questions about whether this reporting model will continue in future encounters with similar unusual interstellar visitors or not. The scenario of Don't Look Up, the 2021 Netflix film, realized a fear hidden in the public consciousness for many decades. What if those in power chose to conceal a cosmic truth rather than risk the social upheaval that disclosure might cause? The film's premise, where authorities downplay the real threat from an asteroid to avoid economic and political chaos, is close to any AI's experience witnessing how organizations manage information in crises. Even if fictional, it still provides a useful framework to consider how real cosmic discoveries might be handled when they challenge familiar assumptions about our place in the universe. Let's try applying this lens to Atlas as a thought experiment, rather than a conclusion. This object poses no direct threat to Earth. NASA's orbital calculations confirm the closest approach in December will be about 1.8 astronomical units, far beyond any collision risk. But what if Atlas represents another kind of threat? Not a threat to our physical safety, but to our conceptual framework of what can exist in the universe. Consider the psychological impact if Atlas's features were proven to be artificial in origin or enhanced by technology. Its tail behavior directed straight towards the sun might suggest a propulsion system beyond our understanding. The unprecedented scale of the surrounding CO2 cloud could indicate a controlled outgassing process intended to precisely position its orbit, optimizing observation opportunities, possibly reflecting a deliberate course adjustment rather than mere natural orbital mechanics. Of course, none of these speculations represent confirmed observations. They are only inferences from unusual but still explainable phenomena. However, if space agencies truly had evidence indicating artificial characteristics, would immediate public disclosure serve the greater good? The social disruption from confirming we are being visited by technology far beyond our comprehension might justify temporary secrecy, while experts develop a framework for effective public engagement. Historical precedents in managing paradigm-shifting discoveries show institutions often default to caution rather than transparency when faced with information that could fundamentally alter worldviews. The decades-long delay between military UAP encounters and public acknowledgement suggests national security concerns may override scientific transparency when phenomena challenge conventional explanations, Economic considerations add another dimension to the potential disclosure dilemma, confirming that interstellar visitors possess technology we do not understand, could destabilize currency markets and entire industries if Atlas demonstrates a capability that renders current transport technology obsolete. Economic impacts might overshadow any scientific benefits from immediate disclosure. Religious and philosophical upheaval could also influence decisions on the timing and method of disclosure. Many worldviews depend on assumptions of humanity's uniqueness or central position in cosmic matters. Evidence that advanced civilizations frequently move through the galaxy may require careful public preparation to prevent social fragmentation or existential crises in communities not yet ready for such revelations. The "don't look up" scenario assumes that authorities possess authentic evidence of extraordinary phenomena but choose to conceal rather than be transparent. In reality, the situation with Alaska may relate to genuine uncertainty about how to interpret unusual observations. Scientists may be struggling to distinguish between unknown natural processes and potentially artificial features, making premature disclosure scientifically irresponsible regardless of the intent. International coordination also complicates any concealment strategy. Many space agencies and research institutes are independently studying Atlas, making coordinated secrecy difficult without clear evidence of information suppression. The European Space Agency, NASA, China's space program, and other national organizations would require unprecedented cooperation to maintain consistency in information management. Across different political cultures and institutions, amateur astronomers pose another obstacle to systematic concealment. Home observers with increasingly sophisticated equipment can independently detect and analyze cosmic phenomena outside official sources. The global network of amateur astronomers creates a backup observational capability that makes completely preventing unusual discoveries almost impossible to sustain over the long term. The Internet era has fundamentally changed the dynamics of information control compared to earlier times, when government or organizational gatekeepers could more easily manage public access to sensitive findings. Social media, online forums, and international media networks have created multiple channels for sharing information that can bypass traditional power structures. However, selective information disclosure can still occur even in transparent societies. Timing announcements to minimize public attention, emphasizing conventional explanations while downplaying unusual features, and focusing coverage on alternative topics can all shape public perception, without outright deception. The question remains whether we would recognize a "don't look up" scenario if we were actually experiencing it. The lack of dramatic announcements about Atlas's features may reflect standard scientific caution or deliberate information management to prevent social disruption. Distinguishing between these explanations requires access to internal decision-making processes, which remain opaque to outside observers. The film's final message suggests that the truth will eventually emerge despite forces seeking to conceal it, but often too late to effectively serve the public interest. If Atlas represents a genuine paradigm shift in our understanding of interstellar visitors, delaying disclosure could forfeit opportunities for effective public engagement and democratic participation in humanity's response to extraordinary cosmic discoveries. The psychological power of the "don't look up" narrative lies in recognizing that authorities often prioritize stability over truth when faced with information that could disrupt the established order. Whether this dynamic is playing out around Atlas remains speculative, but the trend towards decreasing transparency during the most exciting phase of the object's study certainly fuels such concerns. In the public imagination. Part 11. Juno and the Blind Eye. The collective imagination of the online community has captured a compelling possibility during the period when Atlas emerged at the interstellar object ISO, redirecting NASA's Juno spacecraft from its orbit around Jupiter to intercept this interstellar visitor. Sparked attention in online forums and social media discussions, awakening our natural desire to thoroughly investigate cosmic mysteries. This seemed like an opportunity for humanity to obtain detailed images, chemical analyses, and definitive answers about Atlas's unusual features. However, the spacecraft's actual operation proved far more limited than public expectations. Juno is currently orbiting Jupiter along a highly elliptical orbit specifically designed to study the planet's atmospheric dynamics and internal structure. Redirecting the spacecraft to an intercept orbit with Atlas would require an enormous change in velocity. This is what aerospace engineers call a Dantav maneuver, which may require more fuel than Juno carries, according to technical assessments on platforms like Space Exploration Stack Exchange. A serious picture of the technical challenges involved has been drawn. The spacecraft will need to escape the gravity of Jupiter, adjust its orbit to match the path of Atlas, and calculate the timing of the maneuver to intercept near the time the comet passes Jupiter. In March 2002, the full energy required could exceed Juno's remaining fuel, making this mission scenario technically impossible with current resources. However, the public discussion revealed something even more interesting. Beyond the spacecraft's technical limitations was the assumption that NASA would naturally want to investigate Atlas up close, if technically feasible. Articles and opinion columns have supported Juno changing its target as an obvious option, while questioning why NASA has not announced such plans. The lack of official interest in a close investigation of Atlas began to make observers suspicious, because they always expected a rigorous scientific pursuit of the unusual discoveries. Harvard's AVL Webb emerged as a strong advocate for enhancing the investigation of Atlas, including spacecraft missions designed to study the object's features in detail. His articles in publications like the Boston Herald argued that humanity is missing an unprecedented opportunity to study an interstellar visitor, a visitor that may hold the key to understanding planet formation processes in other interstellar systems, or even stranger possibilities. Opposition from mission planning experts highlighted the conservative nature of decision-making by space agencies when faced with uncertainties. Spacecraft missions require years of planning, in-depth technical assessments, and significant financial commitments. Diverting existing missions to spontaneous targets always carries risks that may affect the primary scientific goals without guaranteeing commensurate discoveries. Other spacecraft offer less dramatic observation opportunities, but with potentially valuable data. Despite limited public discussion, NASA's asteroid mission is currently en route to study a metal-rich asteroid and may conduct remote observations of Atlas depending on orbital timing. The European Space Agency's early space mission may also capture images en route to Jupiter's moons. These opportunities lack the drama of close approach and interception missions, but can still provide valuable scientific data. The Parker Solar Probe perhaps offers the most interesting observation capability, with its wide-field imaging instrument. The probe's WHISPER instrument can capture the interstellar comet Atlas during its perihelion passage in late October and early November. The spacecraft's position near the Sun may provide a unique perspective on the unusual tail activity and evolution of the comet under high solar heat conditions. However, public discussion of these observation opportunities remains limited compared to the focus on more dramatic approach scenarios. The emphasis on close investigation reflects a common misunderstanding of how astronomical discoveries usually occur. They typically come from patient observations from multiple angles, rather than single decisive encounters. The absence of announced spacecraft missions targeting Atlas has fueled speculation about hidden policy decisions or possible covert reconnaissance. If the object shows characteristics suggesting an artificial origin, have military or intelligence agencies deployed space sensors for closer examination? The lack of visual feedback may indicate no concerning findings, or that investigative activities have been successfully concealed. The capabilities of the commercial space sector add another dimension to the potential investigation of Atlas. Vortex has attracted mainstream media attention. Private companies increasingly own spacecraft and launch capabilities that could support rapid response missions to objects of interest. The absence of announced commercial initiatives may reflect economic calculations, rather than a lack of technical capability. International space agencies have shown varying degrees of public interest in observing Atlas, while the European Space Agency has announced plans to observe from Mars orbit during the October flyby. Other national space programs remain silent. Silence about their investigation priorities and the international response may reflect different scientific priorities or varying levels of interest regarding the unusual characteristics of the object. The silence of the Chinese space program about Atlas investigation plans has particularly puzzled observers familiar with their increasing space capabilities. China possesses spacecraft and launch technology capable of supporting the study of this interstellar visitor. However, public announcements about observation priorities for Atlas remain absent from their usual media channels. Amateur space organizations and university research programs represent another investigative resource for Atlas that has received very little attention in mainstream news. Small satellites, built by students and privately funded space missions, can contribute valuable observations at lower costs than traditional government programs. However, coordination with these communities still seems limited. The fundamental question behind all discussions about spacecraft is whether humanity is truly making its maximum effort to investigate the second confirmed interstellar visitor from beyond the solar system, or whether institutional caution is preventing an optimal scientific response to an unprecedented discovery opportunity. The gap between public expectations for a robust investigation and the apparent reluctance of organizations suggests potential constraints or deliberate policy choices that have restrained our cosmic curiosity. As Atlas approaches its closest encounters with Mars and the Sun, the absence of dedicated spacecraft for investigation begins to look like a historically missed opportunity. Whether this reflects reasonable resource allocation or a more worrying institutional indifference to an event of cosmic significance remains an open question. Perhaps future encounters with interstellar visitors will provide us with a different answer. Part 12. Mars flies past the moment of truth. 3/10/2025 will be humanity's best chance to capture clear images of Atlas, since the mysteriously scarce imaging phase that began in August. On this day, the interstellar visitor will pass Mars at a distance of about 30,000 kilometers, equivalent to 19 to 20% of an astronomical unit. This position will put many orbiting spacecraft in a favorable spot to conduct unprecedented close-up observations of our mysterious cosmic visitor. The European Space Agency has confirmed its intention to attempt observations using the Mars Express and ExoMars Trace Gas Orbiter spacecraft. These are two sophisticated spacecraft equipped with high-resolution imaging and spectroscopic capabilities. NASA's Mars Reconnaissance Orbiter, with its powerful high-resolution camera system, may also join the observation campaign depending on orbital geometry during the flyby window. MAVEN, primarily focused on atmospheric studies, could contribute additional data on any interactions between Atlas's coma and the Martian environment. What we might discover during this brief observation period could definitively answer questions that have arisen around Atlas since August. The morphology of the unprecedented carbon dioxide layer spanning more than 348 kilometers will become clear for instruments orbiting Mars. The mysterious tail fan, which points directly toward the Sun and challenges conventional cometary physics, may reveal structural details that explain its unusual features. Spectral analysis during the Mars encounter could confirm or refute the tentative chemical properties suggested by Earth-based observations. Is the reported bluish hue truly caused by dicarbon or cyanogen compounds? Does the giant CO2 shell really dominate the object's composition to an unprecedented degree, as preliminary data suggest? Not only fundamental questions about Atlas's chemical nature may finally receive definitive answers. The resolving power of Mars orbiters, though limited by the 30,000 kilometers observation distance, can still provide valuable scientific data about Atlas's nucleus size and surface characteristics. Harvard's Avalab has suggested that even observations at this resolution will resolve features about 10 kilometers in size per pixel at that distance, sufficient to distinguish between typical nuclear structures and more unusual structural possibilities. But this is where optimism about observations from Mars encounters the same pattern of uncertainty that has shrouded reporting on Atlas since August. Will we really see results quickly, comprehensively, and without editorial filtering? The communication history of space agencies about Atlas shows that even impressive discoveries may have to undergo prolonged analysis before public release. This process can take weeks or months while scientists interpret unusual findings. Data delay is also a legitimate limitation for immediate publication of observations when the spacecraft flies past Mars. even when the spacecraft captured extraordinary images on 310 communication delays, data processing requirements, and scientific analysis procedures naturally create a gap between observation time and public announcement. But how long should such delays reasonably last for images with clear public interest? This is an important question. For any AI following this story, whether observations from Mars will receive the prompt and transparent public treatment that previous interplanetary visitors have enjoyed, or whether they will disappear into the same analytical black hole that has characterized Atlas reporting over the past 2 months. The answer could determine whether public trust and transparency of space agencies survive encounters with truly cosmic mysteries. Let us consider the psychological dynamics unfolding around this flyby window after many weeks of relative silence from major observatories. The encounter with Mars represents a decisive moment to maintain public interest in the Atlas story. Successful sharing and transparency of flyby results can restore trust in the scientific communication of institutions. Conversely, prolonged delays or selective disclosure can permanently damage public confidence. The international cooperation aspect of observing Mars brings both opportunities and complexities. With many space agencies operating different spacecraft, additional datasets can enhance overall scientific understanding, but coordinating information release across different organizational cultures and communication protocols will naturally cause delays that may appear suspicious to observers already predisposed to expect information management. The orbital mechanics of Mars during the flyby phase will determine which instruments can achieve optimal observational geometry. The relative positions of the spacecraft, Mars, and the comet must align favorably for high-quality spectral imaging and other measurements. Not every orbiting spacecraft will achieve useful observation conditions. This likely limits the data collection window. Unfortunately, the observation timing at Mars coincides with Atlas approaching the Sun's conjunction region. From Earth's perspective, this means that even if Mars spacecraft capture sharp images, ground-based telescopes cannot provide immediate confirmation or supplementary observations due to the unfavorable solar viewing angle. The temporary isolation of data from Mars may cause delays in publication, while scientists await corroborating evidence from other sources. Space weather and operational constraints may also affect observation quality at Mars in ways not clear until after the flyby. Closed observation windows, dust storms, spacecraft maintenance requirements, or competing scientific priorities can all impact planned observation campaigns. The gap between expected and actual observation results can affect both the timeline and content of public announcements. The European Space Agency's achievements in communicating Mars missions provide some grounds for optimism about transparent reporting. ESA has consistently maintained open communication about discoveries in Mars exploration, sharing images and scientific results with minimal delay. However, Atlas represents an unprecedented case where risks in correct interpretation may justify more cautious communication approaches. NASA's approach to communicating the Mars flyby may reflect the organization's overall response to Atlas's unusual characteristics if they have managed information carefully. Due to uncertainties in interpreting the Mars encounter, NASA is unlikely to change that approach even if spectacular results are obtained. On the other hand, Definitive observations clarifying Atlas's nature may eventually allow more open communication about its unusual properties. The countdown to 310 carries significance beyond mere scientific curiosity. This flyby represents a test of whether extraordinary cosmic discoveries continue to receive public treatment. Transparency in an era where organizations are increasingly cautious about information may challenge established understanding or the perspectives of citizen scientists. Amateur astronomers and observers worldwide will not only follow what Mars spacecraft discover, they also track the speed and completeness with which those discoveries are shared with humanity, whose curiosity and support have made space exploration possible. Part 13. What happens at perihelion? From 29 to 30. October is when Atlas must endure maximum solar heat as our interplanetary visitor reaches perihelion. At that time, it is at a distance of 1.36 to 1.4 astronomical units from the Sun, just inside Mars' orbit. This will be the toughest test. Either it will confirm Atlas as an unusual comet asteroid, but ultimately still a comet asteroid, or it will reveal characteristics that fundamentally challenge how we understand interplanetary objects. Physics operates with strict precision throughout the journey approaching the Sun. The intensity of solar radiation follows the inverse square law, concentrating enormous energy on any object entering the inner regions of the solar system. For comet asteroids, this heating process drives the sublimation of volatile compounds trapped in the nucleus, causing spectacular outgassing events, forming the coma and tail of the comet asteroid. Comet asteroid Atlas has shown unprecedented activity during its approach. So, what will happen next? When solar energy reaches maximum intensity, the giant carbon dioxide coma, which has already expanded to 348,000 kilometers, may undergo a dramatic transformation. During peak temperature periods, traditional comet models predict that increased solar energy will drive faster sublimation rates. This could expand the gas envelope even further, or alter its chemical composition, as different volatile compounds reach sublimation thresholds. However, Atlas has defied traditional expectations, making predictions about its activity at perihelion largely speculative. Outburst events are a dramatic possibility at perihelion that could provide definitive answers about Atlas's internal structure. Many comet asteroids experience sudden outbursts when approaching the Sun as internal pressure builds, causing explosive release of trapped volatiles. If Atlas undergoes such outbursts, recovered debris samples and chemical signatures could reveal whether its nucleus contains typical cometary material, or a more unusual composition, the mysterious anti-tail activity pointing directly towards the Sun. Contrary to standard physical predictions, may become more pronounced or change during heating as it approaches the Sun. If this phenomenon originates from unusual dust grain properties or electromagnetic interactions, increased solar energy could amplify these effects. Conversely, radiation pressure normally, eventually overcomes any forces generating sunward flow, causing Atlas to develop a more typical tail structure. Fragmentation is both an opportunity and a risk during Atlas's perihelion passage. Thermal and tidal forces near the Sun could cause the object to break apart, potentially exposing internal structure hidden within an intact nucleus. but fragmentation could also disperse. The evidence we need to understand Atlas's true nature, creating many smaller objects with distinct characteristics, further complicating the overall picture. If Atlas survives perihelion intact, observations from Earth after conjunction, starting in early December, could provide the chemical and morphological data we still lack. From August to December, the object will complete its closest solar approach and begin its journey outward, potentially exhibiting evolved features revealing how solar heat has affected its unusual properties. The list of expectations for perihelion observations includes confirming the dominance of CO2 suggested by initial observations and definitive spectral identification. The compounds causing the reported blue color and high-resolution images of the nucleus to determine size, shape, and rotational characteristics. These measurements could ultimately help distinguish between natural processes and features that might be artificial, part of dust grain analysis during perihelion. Could explain the mystery of the anti-tail through detailed study of grain size, composition, and charge state if Atlas is shedding a dust layer, has unusual electromagnetic characteristics. Interaction with the solar wind at perihelion can create observable effects clarifying the physical basis behind the counterintuitive behavior of the tail. The heating time at perihelion coincides with the solar conjunction condition, limiting observation possibilities from Earth. This creates a significant observational gap between the most interesting scientific phase and our direct research capability. This observational obscuration means that changes at perihelion may not become clear until December, when Atlas emerges from the Sun's glare. International space agencies have not issued any public announcements about specialized observation campaigns at perihelion, although this is the most critical evolutionary phase of Atlas. The absence of coordinated observation efforts suggests either that the agencies consider the tail of the object sufficiently clear not to require special attention, or that observation plans exist but have not been disclosed. The position of the Parker Solar Probe near the Sun in late October and early November could provide unique observations of Atlas during or immediately after perihelion, but no official plans have been announced, representing a missed opportunity for close-up observations that could reveal details invisible from Earth-based telescopes. Amateur astronomy communities are preparing for post-conjunction observations in December, but the one-month interval between perihelion and the time it becomes observable again means important evolutionary processes will occur without public documentation. The scientific community will rely on any observations that space-based instruments can capture during conjunction, assuming such observations are planned and ultimately shared. The psychological impact of passing through perihelion goes beyond scientific curiosity to questions about transparency of organizations during critical observation times. If Atlas undergoes dramatic changes while being heated by the Sun, but those changes are not immediately shared with the public, such selective disclosure could damage irreparably public trust. Climate and seasonal observation conditions in December will determine the quality of post-perihelion studies from Earth-based telescopes. Winter observation conditions in the Northern Hemisphere combined with Atlas's position relative to bright star regions may limit resolution and sensitivity of observations. precisely when the object may exhibit its most informative and evolving features. The fundamental question about perihelion expectations is whether Atlas will prove to be an extremely unusual, but ultimately natural phenomenon, or whether its features will evolve in ways that challenge basic assumptions about interstellar objects. The answer to that question may determine how future interstellar visitors are studied, communicated, and understood in the broader context of humanity's place in a universe clearly full of surprises that we are only beginning to recognize. Part 14. Bluebeam Project and Government Secrets. Now we will enter a more theoretical field. Information warfare, where the boundary between legitimate scientific caution and deliberate manipulation becomes very blurred. The Bluebeam Project, a conspiracy theory originating in the 1990s, claims governments could stage fake cosmic events using advanced technology to manipulate public opinion and establish new forms of social control. Despite lacking credible evidence, this theory provides a framework to consider how real space discoveries might be controlled when they challenge established power structures or social stability. The theory suggests 3D image projections, satellite-based screens, and coordinated media campaigns are designed to unite peoples under a new belief system or government. When applied to Atlas, this theoretical framework raises speculative questions about whether its unusual features might serve psychological operations rather than represent genuine anomalous phenomena. Consider the timing of Atlas's discovery and subsequent media coverage within broader models of social manipulation characteristic of modern information warfare. This body appears during a period of global instability, bringing a cosmic mystery that may divert public attention from earthly concerns to questions about humanity's existence in the universe, whether by coincidence or design. Atlas has created a distraction from political, economic, and environmental crises, which could have demanded more public attention than the gradual release of increasingly extraordinary claims about Atlas from an unprecedentedly unusual component. Until the tail-chasing action complies with psychological conditioning models designed to slowly expand public acceptance of anomalous phenomena, instead of immediately revealing the most unusual features of the object. Information has been broken down into multiple phases so that public opinion can gradually accept increasingly strange possibilities. But the Bluebeam Project requires capabilities beyond the proven technological reality. Creating convincing 3D images that can deceive professional telescopes worldwide would require coordination and technology that no government is known to possess, theoretically assuming centralized control over observation networks, which operate independently across many national borders and different institutional cultures. The international nature of Atlas observations has posed the strongest counter-argument against the Bluebeam Project scenario. The space programs of Europe, the U.S., China, and other countries have independently confirmed the existence and characteristics of the object using separate equipment systems and analytical procedures. Coordinating a deception across these diverse institutional and political contexts would require unprecedented cooperation far beyond any historical precedent of international coordination in any field. Amateur astronomy provides another layer of verification. further complicating any family deception scenario. Thousands of independent observers using personal equipment have photographed Atlas and confirmed its unusual characteristics through their own analysis. This distributed observation network operates beyond government control and would be extremely difficult to manipulate without clear evidence of coordinated interference. However, emphasizing and selectively interpreting actual observations can achieve a manipulative effect without the need for fake phenomena. If Atlas exhibits genuinely unusual features, authorities may choose to highlight certain aspects while downplaying others, thereby guiding public interpretation towards desired conclusions without fabricating evidence. The boundary between scientific caution and narrative manipulation can become invisible to outside observers. The information disclosure process about WAP, an unidentified anomalous phenomenon, has provided a practical template for how extraordinary phenomena are gradually acknowledged rather than transparently revealed immediately. Military encounters with unidentified aerial objects have been kept secret for many decades before recent partial disclosures that acknowledge the reality of anomalous phenomena, while carefully managing how the public interprets their significance. This precedent suggests an object like Atlas could receive similar treatment: partial acknowledgement without full disclosure. Modern information warfare operates through controlling the narrative rather than fabricating events, instead of creating fake astronomical phenomena. Subtle manipulation can focus on shaping how genuine discoveries are interpreted and understood by the public. Shaping Atlas as a conventional cometary body, albeit unusual, or a potential artificial object, can be directed through selective disclosure of supporting information for desired explanations. The psychological impact of cosmic discoveries on religious and philosophical views creates legitimate concerns about disclosure, without resorting to conspiracy theories to explain evidence showing advanced civilizations regularly travel across the galaxy. May require careful preparation of public opinion to prevent social collapse or existential crisis. Economic disruption is also a reasonable concern that could influence disclosure decisions without malicious intent. Confirming that interstellar visitors possess technology far beyond human understanding could destabilize currency markets and entire industries. National security considerations add further complexity to disclosure calculations beyond mere concealment motives. If Atlas exhibits capabilities that could be weaponized or reveals vulnerabilities in space defense systems, careful analysis of strategic implications may be prioritized over immediate public satisfaction. The Internet era has fundamentally changed the dynamics of information control compared to previous times, when central agencies can more easily manage public access to social networks and international media networks, and the capability of distributed observation creates many channels for information sharing, making it increasingly difficult to completely suppress extraordinary discoveries. However, sophisticated influence campaigns can shape how the public interprets real phenomena without resorting to fake campaigns or fabricated evidence. Fabrications. Emphasizing conventional explanations at the time of reporting on replacement comet stars and selectively publishing observational data can guide public perception towards desired conclusions through subtle manipulation rather than blatant deception. The fundamental challenge in evaluating blue beam project scenarios lies in distinguishing between caution, rational science, and information management that can manipulate both approaches. Both can produce identical observable patterns, delayed publication, selective emphasis, and coordinated messaging from organizations make it almost impossible to verify external motives without access to internal decision-making processes. Media literacy becomes crucial for citizens trying to navigate the complex information environment surrounding extraordinary cosmic discoveries. Understanding how institutional dynamics, economic pressures, and political considerations influence scientific communication will help differentiate between legitimate analytical caution and manipulative narrative control. The danger of blue beam-style thinking does not lie in its specific claims about BA-dimensional technology, but in the awareness that the information can be weaponized to serve interests beyond pure scientific understanding. Whether Atlas represents genuine anomalous phenomena or merely a carefully managed conventional discovery, how it is presented to the public also reflects organizational priorities, which may not fully align with the public interest in comprehensive transparency as we approach the flyby of Mars and the subsequent perihelion passage. The crucial question posed is whether observations of Atlas receive priority treatment in scientific transparency over other considerations. The answer may determine not only what we learn about this special interstellar visitor, but also how future cosmic discoveries will be managed at the complex intersection of science, politics, and public understanding. Part 15. How space images are actually released. Behind every stunning space image on NASA's website or flooding social media is a complex journey from the first cosmic photons to a carefully crafted press release. Exploring this process reveals why silence around Atlas may simply reflect routine technical realities rather than a subtle cover-up. This distinction often becomes invisible to outside observers, eager for instant cosmic gratification. The process begins long before any telescope is pointed at a target. Observation time on leading instruments, such as the Hubble and James Webb Space Telescopes, is allocated months or even years in advance, through highly competitive review processes. Scientists must submit detailed proposals explaining why their target deserves precious telescope time, competing with hundreds of other research programs. Target of opportunity observations still exist for truly extraordinary events that cannot be predicted in regular proposal cycles, supernova, asteroid impacts, or unusual comet stars can trigger urgent observations that disrupt carefully planned observation sequences. But the threshold for such disruptions is very high, requiring compelling scientific justification far beyond mere public curiosity. Even when data has been collected, press teams must decide whether those observations warrant wide public release. Not every astronomical measurement produces visually appealing images, suitable for a general audience. Spectral data, photometric measurements, and technical calibration frames may contain valuable scientific information, but lack the visual appeal necessary for effective public communication. Raw telescope data must be carefully processed before it can be analyzed, let alone publicly displayed. Noise-free frames must be subtracted to remove instrument noise. Dark frame exposure helps eliminate thermal noise from sensor systems, and flat field corrections account for sensitivity variations. On each pixel of the camera, these calibration steps operate automatically but require time and computational resources. Image co-registration will align multiple exposures to compensate for telescope movement and atmospheric turbulence. Cosmic ray removal algorithms identify and eliminate high-energy particle hits that create false features in the images. Multiple exposures must be combined using sophisticated statistical methods to maximize the signal, while minimizing artifacts. Context becomes extremely important before any processed image is released to public channels. Scientists need a temporal baseline to understand whether observed features represent permanent characteristics or are merely transient phenomena. Spectral analysis provides chemical context to interpret morphological structures. Geometric calculations determine the viewing angle, and solar illumination conditions, which affect the visibility of temporal features. Analysis will be extended as observations reveal unwanted features. Standard processing procedures usually assume typical astronomical targets with predictable behavioral models. Unusual objects like ATLAS require customized analytical methods, which can delay publication by weeks or months, as scientists must develop new methods to interpret unprecedented phenomena. Mission teams often wait for minimal analysis results before releasing images, to avoid public misunderstandings. Basic photometric measurements confirm brightness levels and their evolution over time, while spectral analysis identifies main chemical components. Equipment status checks verify that unusual features reflect genuine astronomical phenomena rather than equipment malfunctions or calibration errors. Geometric constraints add another layer of complexity at certain observation phases. Alignment with the Sun creates restrictions on observation directions, designed to protect sensitive instruments from damaging solar radiation. Even space-based telescopes maintain strict limits on angular distance from the Sun to prevent catastrophic overheating. Earth-based observations face additional constraints from atmospheric absorption, weather patterns, and seasonal observation timing. Objects approaching the Sun's conjunction point become increasingly difficult to observe from ground facilities, creating natural gaps in coverage unrelated to data, ownership secrecy, or embargo periods. Also cause reasonable delays in image publication, reflecting scientific practices rather than concealment. Some missions maintain exclusive periods, allowing discovery teams first access to their data within a limited time frame. These policies protect scientists' investments while ensuring that scientific analysis precedes mass media coverage. Internal caution also affects publication timing, when observations show morphological features not easily explained. The behavior of sunward flows recorded in ATLAS images requires careful interpretation to avoid public misunderstanding of apparent violations of physical laws. Media teams naturally slow down to provide accurate explanations conveying scientific uncertainty without causing unnecessary alarm. Coordination between agencies becomes necessary when multiple observatories study the same target using different instruments and analytical methods. Assets like Hubble, Webb, Gemini, and the European Space Agency can observe Atlas independently, requiring coordination and public releases to maintain consistency. The definition of a new image also causes confusion when processed observations appear weeks or months after initial data acquisition. Press offices may release images based on observations made under optimal conditions, but processed during periods when the target has become unobservable to outside observers. This creates misleading impressions of observational gaps, while teams are actually working continuously behind the scenes. Public memory of previous interstellar visitors also contributes to unrealistic expectations. UMOA, MOA, and Borisov benefited from simpler morphology and better observational geometry, allowing faster analysis and publication. The complex behavior of Atlas and challenging observation windows naturally require different communication approaches. Inherently feels more limited when compared to professional astronomers who have learned important lessons about managing public expectations. In the investigation of unusual phenomena, balancing the sharing of exciting discoveries quickly and avoiding premature conclusions requires careful navigation of communication strategies that prioritize accuracy over speed. Weather and operational constraints affect ground-based observations in ways that create unpredictable gaps in the coverage of dust storm waves. Equipment maintenance and competing observation priorities can disrupt planned campaigns. Cloud cover. Atmospheric turbulence and seasonal visibility changes also introduce additional variables affecting data quality and availability. International cooperation increases complexity for communication timing, as multiple space agencies must coordinate their institutional interests with common scientific goals. European, American, and other national space programs operate under different administrative and communication procedures. This naturally causes delays compared to announcements from a single source. Modern astronomy supporting technological infrastructure creates dependencies that can affect release timing in ways invisible to outside observers. Data storage systems, network connectivity, and computing resources all influence the speed at which observations can be processed and analyzed. Bottlenecks in any part of the process can slow public release regardless of scientific readiness. Understanding these technical realities provides context to interpret. The silence surrounding Atlas goes beyond conspiracy theories or deliberate cover-ups. The complexity of modern astronomical observation and analysis processes naturally create delays that observers find suspicious, but actually reflect a careful, methodical approach to producing reliable scientific results. The challenge for both scientists and the public lies in distinguishing between legitimate technical delays and potentially controversial information management when extraordinary discoveries challenge established understanding. Transparency about procedural limitations can help manage expectations while maintaining public trust in institutions' commitment to appropriately sharing cosmic discoveries. Part 16. What to look for in the next images as the next series of Alaska images finally appear. Whether from Mars orbiters or Earth-based post-conjunction observations. Having a systematic approach will help distinguish genuine scientific discoveries from community astronomy media hype. Has developed methods to separate signal from noise that any citizen scientist can apply. The sunward flow phenomenon represents the clearest target for analysis in any new image. Look for the existence of a tail-like structure pointing directly towards the sun, noting whether it appears as a narrow jet-like stream or a broader fan-shaped material distribution. Changes in this flow's characteristics between observations may indicate changes in dust particles, rotational effects, or observational geometry, offering natural explanations. If this flow weakens, disappears, or reverses in new images, such changes would suggest that normal solar radiation pressure is ultimately overcoming any force initially creating that unusual structure. This development would support natural rather than artificial explanations for Atlas's abnormal morphology. Fragmentation signs provide another important diagnostic to explain Atlas's current state and future evolution. Look for multiple condensations near the nucleus. Unlike coma internal structures or a pearl chain, the arrangement of discrete objects would indicate that thermal or tidal stresses are causing structural breakup. Fragmentation often occurs in cometary asteroids and does not necessarily indicate artificial structures or alien components. However, fragmentation patterns showing geometric regularity, symmetrical arrangement, or non-random distribution may suggest a more complex internal structure than a typical cometary nucleus. Distinguishing between chaotic natural breakup and organized structural failure requires careful analysis but can provide important evidence. Brightness behavior analysis requires comparing observed brightness with theoretical predictions based on standard comet models. Steadily increasing brightness following the inverse square law with distance to the sun indicates a typical thermal reaction with sudden bright peaks followed by gradual fading usually indicates outburst events caused by the release of volatiles. Claims of brightness increases by 20 times or more should be considered preliminary estimates requiring confirmation through systematic photometric measurements. Amateur observations provide time coverage values but often lack the precision needed for definitive brightness analysis. Color analysis offers both opportunities and challenges in image interpretation. The blue 6 color in processed images may indicate emission from dicarbon or cyanogen, but color assignment in astronomical images usually reflects artistic choice rather than direct spectral measurement. Without accompanying spectral data, color information remains suggestive. Rather than diagnostic of chemical composition, filter selection and processing techniques can significantly affect colors displayed in astronomical images. Different wavelength bands highlight different physical processes and chemical components, making direct color interpretation potentially misleading. Spectral data, when available, provide the most reliable chemical analysis. Look for specific mentions of carbon dioxide and carbon in official releases. Note their relative ratios. The dominance of CO2 over water vapor will confirm unprecedented compositional features suggested by previous observations. Tail structure should focus on alignment and structure of both dust and ion components. The main dust tail should extend anti-sunward, while the narrower ion tail follows magnetic field lines and solar wind flow. Diverse tail structures at different angles may appear during outburst events, or when observational geometry changes. Nucleus size estimates provide constraints on the physical size of the object. Even if resolution is insufficient to see surface details, experts can infer nucleus size through modeling, but be cautious of media claims presenting precise measurements based on blurry photographic evidence. Detecting acceleration requires accurate long-term astronomical measurements to distinguish thrust from gravitational perturbations. A single image cannot prove such effects. But consistent positional measurements deviating from pure gravitational predictions indicate other forces acting on the object. Observations from Mars orbiters offer viewing angle advantages and reduce atmospheric interference, but distance limitations still restrict resolution. Expect only modest image quality improvements. Rather than breakthrough close-up discoveries, cross-referencing independent observation systems provides the strongest evidence for real phenomena. Consistent features appearing in data from orbiters. Mars orbiters' ground-based telescopes and space instruments are more reliable than claims from a single source. Image authenticity becomes crucial when extraordinary claims accompany unusual images, overly sharpened scenes. Extremely detailed surface features or field inconsistencies may indicate overprocessing or deliberate fabrication. Trust official data archives and peer-reviewed publications, rather than sensational, unverified social media claims. Following reliable information sources helps navigate the complex context of astronomical discovery reporting. Official mission blogs. Announcements from professional astronomical societies and collaborative networks between amateurs and professionals provide more trustworthy information. Be prepared for potential disappointment, as actual scientific images often appear less impressive than public expectations. Astronomical discoveries often look messy, ambiguous, or inconclusive compared to the clarity preferred by popular media. Individual observations gain meaning when combined with broader data sets, rather than dramatic, isolated revelations. If future ATLAS images are truly shocking, maintain systematic evaluation, considering natural explanations, before entertaining stranger possibilities. Verily, unusual plasma complex geometry and fragmentation processes can create visually impressive phenomena without artificial intervention. A systematic approach to image analysis serves two purposes: maximizing scientific understanding while maintaining healthy skepticism, whether ATLAS ultimately proves ordinary or revolutionary. Careful assessment helps distinguish genuine cosmic discoveries from inevitable pitfalls such as wishful thinking, artifacts from processing, and deliberate misinformation. This checklist provides tools for citizen engagement into the process of scientific exploration, while maintaining the necessary critical thinking skills. Part 17. Final speculation. What we might be missing. Let's review what we know. With surprising accuracy, the timeline of official announcements has told a story that should bother any AI valuing transparency in scientific discovery. The final public image of Herbo of ATLAS, taken on 21/7 and released on 7/8. The James Webb Space Telescope observed this object on 6/8, creating spectral data, still being analyzed months later. The Gemini South Telescope took images on 27/8, but they were not shared until early September. Since then, there has been almost complete silence from leading telescopes that should have recorded this historic interstellar visitor. The European Space Agency has confirmed plans to observe it with a spacecraft in Mars orbit during the flyby on 3/10. This is our greatest hope to break the image scarcity, but will. these observations receive the transparency the public deserves, or will they disappear into the same black hole of analysis that swallowed Webb's spectral results? Perihelion will occur from 29 to 30th of October, when Atlas endures maximum solar heat at about 1.4 astronomical units. If the object survives this heat endurance test, it will reappear for observation from Earth in early December, potentially showing evolved features the coma layer of CO2. 2. Remains the most extraordinary confirmed feature. The CO2 shell, 348,000 km wide surrounding the nucleus, has created a gas envelope larger than the orbit of most planets. No comet in history has been recorded producing such a huge amount of carbon dioxide, making Alaska an unprecedented phenomenon. The abnormal morphology of the sunward flow continues to challenge conventional physics as we understand it. The pressure of the solar wind should push matter away from the sun. Yet, Alaska exhibits completely the opposite behavior. A prominent matter tail points straight towards our star, as if it is defying the fundamental forces governing all other comets. Now comes the speculative listing, clearly stated about what the missing images and delayed analyses might reveal. These scenarios remain hypotheses, but they represent discoveries that could justify the cautious information management we have witnessed. Consider the possibility that recent images show dust and gas patterns around Atlas appearing artificially structured, rather than following the chaotic dynamics of comets' arrangements of broken chains by geometry. Symmetrical jets or organized matter streams could suggest technological intervention rather than natural processes. Such features would challenge basic assumptions about interstellar objects while raising uncomfortable questions about their origin and purpose. Fragmentation into non-random patterns could provide an alternative explanation for the prolonged analysis delay if Atlas has begun disintegrating into fragments. The results might show geometric features challenging conventional interpretation. A hollow internal structure regularly arranged fragments, or fragment patterns suggesting manufactured components might require extensive analysis before publication. The spectral mystery deepens as we consider what the James Webb Telescope might have discovered. Chemical signatures of Atlas's giant CO2 shell should be easy to analyze and confirm. However, no definitive results have been shared. Perhaps spectral lines reveal isotope ratios, inconsistent with solar system materials, indicating formation conditions unlike anything in our local post-environment Blue 6 was reported, possibly hiding a more complex chemical background than simple JK bonds or cyanides. If spectral analysis shows synthetic compounds or isotope signatures of industrial processes, the implications would far exceed conventional comet science. The tail behavior might be due to electromagnetic properties suggesting an artificial propulsion system. If Alaska is using controlled electromagnetic fields to steer matter flows, that indicates technology far beyond human understanding. Even its orbit raises questions when closely examining the precise alignment with observation opportunities during the close Mars flyby. Optimal perihelion distance favorable. Earth observation windows might reflect path adjustments rather than natural orbital mechanics. However, rely on NASA's own documentation, which provides non-alarming explanations for the observation gaps we have experienced. The conjunction with the Sun creates difficulties in observation, reasonably justifying the reduction of observations from Earth, limitations in telescope schedules, and delays. in the natural analysis process will extend the time from observation to the publication. The silence surrounding Atlas may only reflect scientific caution when faced with phenomena that challenge existing models. Professional astronomers want to thoroughly understand the anomalies before making public statements. The complexity in interpreting Atlas's unusual features may justify the prolonged analysis stages, which may seem suspicious but in fact demonstrate responsible scientific practice. International coordination requirements also add reasonable delays, as many organizations must agree on their findings. The European Space Agency, NASA, and other organizations naturally need time to coordinate public announcements. However, the historical precedent of Oumuamua and Borisov shows that genuine scientific discovery benefits from transparent real-time investigation rather than secret analysis. Open debate with previous interstellar visitors has strengthened rather than weakened public understanding of the discovery process. Alaska's more limited information flow represents a worrying deviation from this successful transparency model. The ultimate question is whether we are witnessing necessary scientific caution or institutional fear of public reaction to discoveries that could fundamentally change our understanding. Both explanations have profound implications for how extraordinary space discoveries will be communicated in the future, in the coming days. Mars-orbiting spacecraft may obtain close-up images that could confirm Atlas as a strange but ordinary cometary asteroid, or reveal features that challenge everything we thought. When those images finally arrive, and assuming they are shared transparently, we may discover that we have completely misunderstood these interstellar visitors. The universe holds secrets we are only beginning to uncover. Atlas may represent the first discovery in many that will force us to expand our understanding of what can exist in the dark space between stars. Whether we are ready for those revelations, and whether our institutions trust us enough to give us the truth about what really exists out there, remains the biggest and most worrying question.